Hi, my name is David Norris, and I'm a stay-at-home dad to an amazingly beautiful Rett daughter. I spent the last few years researching and reading countless papers on Rett and autism, and I want to talk to you about something that I'm grateful I found during my research. I didn't know my daughter was suffering from dysfunctional brain cholesterol. When I hear cholesterol, I think heart disease, but the brain has a completely different relationship with cholesterol than the rest of your body. And in Rett syndrome and in autism, this relationship is broken in ways that most people aren't talking about. Here's the first thing you need to understand. The cholesterol in your brain cannot come from your blood. The blood-brain barrier blocks it. Your brain has to make its own cholesterol entirely from scratch. And it does this constantly because your brain is approximately 6% fat, and a huge portion of that fat is cholesterol. Why does the brain need so much cholesterol? Two main reasons. First, myelin, the fatty sheath that wraps around every nerve fiber like insulation on electrical wire. Myelin is roughly 70% cholesterol. Without adequate cholesterol synthesis, myelin degrades, nerve signals slow down and become unreliable and misfire. Second, lipid rafts. These are tiny cholesterol-rich platforms within the neuronal membrane where receptors cluster and function. NMDA receptors, which are already immature and dysfunctional in Rett, sit inside lipid rafts. If the cholesterol that forms those rafts is inadequate, the receptors destabilize further. You're adding structural problems on top of a genetic one. In Rett syndrome, the MECP2 gene directly regulates and controls cholesterol synthesis in the brain. When MECP2 is lost or dysfunctional, those genes are suppressed. The brain makes less cholesterol, myelin thins, lipid rafts destabilize. This is measurable in Rett mouse models and in patient tissue. In autism, the picture is more variable, but a significant subset shows dysregulated sterile metabolism. Some genetic autism subtypes have severe cholesterol synthesis impairment as a core feature, not just a side effect. Now here is where it gets connected to something else I wanted you to understand. Aldehydes. The brain's fats, especially DHA and arachidonic acid, are extremely vulnerable to oxidative attack. In Rett, mitochondrial dysfunction creates excess reactive oxygen species. These attack the brain's polyunsaturated fats in a chain reaction called lipid peroxidation. And when those fats break down, they release toxic byproducts called aldehydes. These aren't just waste products, they're actively damaging. They're modifying proteins, disabling mitochondrial enzymes, and creates aggregates that cells can't clear. And Rett doesn't clear these aldehydes efficiently either. Normal clearance requires glutathione, aldehyde dehydrogenase enzymes, and an NRF2 pathway, all of which are deficient in Rett, and aldehydes accumulate and keep damaging. So what do you do about all of this? You protect the brain's fat from the inside out. Squalene, an olive-derived compound, acts as a sacrificial antioxidant in lipid environments. Reactive oxygen species react with squalene preferentially before they can start the peroxidation chain on DHA. It also supports the cholesterol synthesis pathways as an upstream precursor, giving the brain building material for myelin and lipid rafts. Sea buckthorn oil contains tocopherols, vitamin E family, that breaks the peroxidation chain reaction at a different point. Where squalene prevents initiation, vitamin E stops propagation, and these work together. DHA itself is essential. It targets peroxidation, but the answer isn't to withhold it, the answer is to protect it. A brain without DHA is worse than a brain with DHA that needs protecting. L-carnosine directly quenches 4-HNE and malonide through a process called carbonyl quenching. It binds to the aldehyde group chemically and neutralizes it. It also specifically protects EAAT2 from aldehyde modification, addressing the same transporter your amino acid supports through completely different angles. Benfotiamine A fat-soluble form of B1 supports the aldehyde dehydrogenase enzymes that clear aldehydes through enzyme pathways in the bloodstream. The regular water-soluble B1 in a B complex doesn't reach the lipid environments where this damage is happening. Benfotiamine does. TTFD, the brain-penetrating form of B1, unlike standard thiamine or benfotiamine, TTFD crosses the blood-brain barrier and delivers thiamine directly to the neurons that need it most. Once inside the brain, thiamine is a critical cofactor for the aldehyde dehydrogenase enzymes that clear the toxic aldehyde byproducts. These accumulate when membrane lipids are damaged by oxidative stress. When the brain's cholesterol and phospholipids architecture is under attack, the aldehydes generated from the damage need to be cleared quickly. TTFD is supporting the enzymatic machinery that does this exactly. And I would give that in the morning time, and small amount of fat for absorption. Sulforaphane is one of the most powerful tools we have for protecting brain cholesterol from oxidative damage. It activates the NRF2 pathways, including the aldehyde dehydrogenase enzyme that neutralizes the toxic 4-HNE and acrolein produced when membrane lipids are attacked. What I'm describing is daily structural support. This is keeping the brain's physical architecture intact. The myelin, the membranes, the receptors, in a condition where the genetic blueprint for maintaining that architecture is compromised. You can't fix the gene, but you can support the environment the gene is supposed to be maintaining. I hope this helps. Have a good day. Thank you.